Thank you for coming to my presentation on concurrency for web developers. A better title would probably would have been concurrency for JavaScript developers, as I'll be using JavaScript for examples for both like backend and front. So yeah, oh, and by the way, my name is Brandon Lee. So before I dive into the meat and potatoes of the presentation, I just want to briefly talk about my motivation for giving this presentation in the first place. So I currently work as a software engineer at MongoDB on the documentation platform team. And so what that entails is kind of working on the internal tooling around the documentation site and just maintaining the documentation site itself. And so a project that I've been working on the last few months is improving page load speeds and in particular improving core web scores, especially due to the fact that Google, or the impetus for focusing on this project, and this project even coming to fruition is due to the fact that Google recently changed the core vital scores. So they recently introduced a new core vital called Interaction Next Paint, and this replaces first input delay. And for those of you who do not know what first input delay is, essentially what it represented was the amount of time it took after you could click on a page and for it to be interactive. The issue with that metric is that pretty much every site scored perfectly on the specific metric, so it wasn't really telling you much. So Google came up with a new metric called Interaction Next Paint, or INP for short, which represents the amount of time it takes before before you can the site is interactive after making a previous interaction. And this is for any interaction throughout the site. And the reason why this ties back to the idea of concurrency is that during my time looking at different solutions, specifically I work with React and front end, I stumbled across a lot of specific implementations of concurrency for React, and more specifically to React 18 introduced this idea of concurrent React. And I don't want to get into too much detail yet because later on in the presentation I'll be doing a live demo so you can see in real time like how this works and so forth. So yeah, before I go on, I'm just curious, I feel like a raise of hands, how many people work with React? Okay, should go a lot of people, perfect. How many people work with Node.js on the back end? Perfect, great. So hopefully this presentation is useful for everyone. So that's another thing too, I really wanted this presentation to be more hands-on and kind of more practical, so there's real world usage that you can maybe get out of this, hopefully. So I'll be light on the slides, and I'll go kind of briefly over the high level theory and maybe go more in depth later on if need be. But yeah, so let's just start off with the basic theory behind concurrency. So let's answer the basic question, what is concurrency? So a common misconception is that concurrency is the same thing as parallelism, but concurrency doesn't necessarily equal parallelism. I found this really great quote online from the co-creator of Golang, Rob Pike, where he talks about concurrency is dealing with many things at once, whereas parallelism is about doing many things at once. So I was kind of having a conversation with my cousin, he's a non-technical person, but I wanted to kind of bounce off the ideas behind his presentation and see if I could convey it to him. And he kind of came up with a good analogy that I wanted to share too, which was, especially in the context of JavaScript, which for both like the back end and front end implementation, only has a single thread, right? Concurrency kind of works like a single chef in the kitchen. So, for example, say you're working at a restaurant and you receive an order and you're working as like a chef, right? A tick comes in and it's for a steak. So, if you were to do things synchronously or like in a non-concurrent manner, you would cook the steak in the pan and wait till it was done cooking before you even started another order. So say as you're cooking the steak or waiting for it to cook, maybe it needs about like 3 minutes before you have to flip it over and sear the other side. Orders are coming in, an order for a burger comes in. But again, in the synchronous fashion, you would not be even starting another order. You're just standing there waiting for the steak to be ready to flip. And so that's clearly not a sensible way to work as a chef. So you put the steak on the pan, you let it sear for 3 minutes on one side, but during the meantime, you're free to do other things. So you start, you put the burger on the grill, right? And you maybe like toast the bun, etc. So that's kind of like hopefully the mental model I want to impart for like how concurrency works in JavaScript. There's one thing actually doing work, but you can kind of wait for things that don't need to be worked on or there's nothing for you to do in the moment. and do other things that you can do right now. So yeah, that's kind of what concurrency is. So I just want to briefly also talk about the JavaScript event loop in a pretty abstract level. So the JavaScript event loop has nuances and differences between like different platforms and even different browsers. So for example, the front end, so the Chrome's event loop looks slightly different than the Node.js event loop. But for the sake of this presentation, we won't dive into the exact nuances, as the general principle is more or less the same. So a JavaScript program has objects memory allocated on heap, which is fairly standard. But the components that we want to focus on is the call stack and the queue. So the call stack represents synchronous work that currently needs to be done. So say, for example, your program has a function that's being called or a console.log statement that is being called, that happens all in the stack. The queue represents tasks that need to be completed at maybe another point in time. So for example, you have a set timeout. So this will, once you call a set timeout, it kind of hides in the background, and once that timeout has kind of finished, it gets added to the task queue. So specifically, the queue is a task queue. And then once the call stack has been cleared, there's no other operations for the call stack to perform. A message is read off the queue, and then the call stack will execute everything that was in that task. That's like the general idea of this single-threaded event loop. One key thing to note too, the reason why JavaScript doesn't need to wait for certain processes is this idea of non-blocking I/O. Out of curiosity, just another raise of hands, how many people are familiar with the idea of non-blocking I/O? Okay, good, a couple of hands. So for those of you that are not familiar, the idea of non-blocking I/O is that certain operations, so I/O stands for input and output, they don't need to wait because nothing is being done. So for example, a network request is like a form of I/O, right? So if you make, I'm sure that many of you who've worked with JavaScript at all have had to make an Axios request, right? You do a GET request to some URL. During that time when the request is being made and sent across the network, the thread doesn't need to do anything. It's just waiting for the response to come back. So instead of blocking, which means you wait for the response to come back before you do anything else, kind of like waiting for the steak to cook for however long, like 6 minutes, you actually let the network request do its thing and then take on some other tasks in the meantime. And then when the request comes back in, you process it at that point when it's ready. So yeah, that's basically it for the high level theory. So let's move on to the demonstration. So one thing I want to talk about, or what the first part of the demonstration will be on the backend side. So we'll be looking at a Node example. So before I dive into the actual Node.js code, I want to just briefly talk about going back on the idea of non-blocking I/O. So JavaScript, if those of you, or Node.js specifically, if those of you are familiar, has a library called FS, which stands for file system. And there are synchronous methods and callback versions of various file system operations. Like for example, reading a file. One common mistake that I made in the past, and I think that's actually, I see fairly frequently, is people use the sync methods. And I want to demonstrate why that's less than ideal, especially in the context of a RESTful API, right? So we'll have, in the backend example, we'll have an express application that's like a sync endpoint that returns the contents of a file. First, using a sync method approach, and using an async approach. So let's go ahead and do that. So right here, I have index.ts. It doesn't do anything too crazy. And does this look good? Would you like me to zoom in at all for this? Looks good? Okay. So, what did you say? Oh yeah, of course. What's this really quick? So yeah, so this is a very straightforward API. There's currently one endpoint called sync, which has a query parameter file, and we take this query parameter to get the file name, and then we use read file sync to actually read the contents of the file and send that back as a string to the user. So let's go ahead and run this here really quick. Actually go to the right directory. Okay, beautiful. So just to demonstrate what the response should look like, it should look something like is just a bunch of markdown. So for more context too, there's a bunch of markdown files in here which I'll be using for the benchmark portion of the code. So essentially what the benchmark portion of the code is doing is reading all these files from the assets directory and then making a request to that endpoint. And right now it's just making a call only to the sync directory. So we read all of the files here, markdown files here, and then we perform this task, and then we have some timers to show us how long it takes. So let me close this out. Back to this. And let's do the benchmark really quick. So again, you can run benchmark, we'll see how long it takes. So right now it takes about 52 milliseconds for the sync approach, which not too bad. But again, this is a pretty contrived example. On my, I'm sending a request to my own local machine, so there isn't any network delay really. So it's going to seem a lot quicker here in this context. So, but again, as previously mentioned, going back to the steak, the chef example, cooking the steak. Essentially what we're doing here is that if multiple requests come in, other requests can't even start being processed until the read file sync function call is completed for a previous request. So if one user makes a request at endpoint and they're calling read file sync, another requests come through, those other requests don't even start to be processed, and you don't even, those requests don't even start processing the read file requests, because again, with reading content from the disk or the hard drive, it's also not blocking I/O, because there's a period of time when you're reading stuff from the hard drive where the hard drive is doing some work and you have a little bit of time to do some other stuff. And again, this is really, really fast because SSDs are incredibly quick, so it's a really small window of time, but it's a little window of time to do other work, to at least get started on processing another file. So let's go ahead and do an async approach to this endpoint and see how well it performs. So what we can do, so the file system library has a callback version of this read file, but that's a little bit less ergonomic, so there's a way to promisify it to make it so you can do a wait and get the file content back like you would more traditionally do. So there's actually a useful function called promisify, which I can just import. Promisify. Okay, and then I will create a promisify version of the read file function. Okay, and I'll create a new endpoint called async. And then this portion is pretty much identical, so it's above file and create there. And then now I'll call read file async. I should await this. I forget. I'm just gonna copy this. I should probably get on this previously, but okay, it's fun type. Okay, so now we have the content of the file as a buffer, and we can call toString like above. And now we have our async endpoint. Let's go back to the benchmark code and uncomment this test here. Let's go ahead and run the benchmark. I practiced this a bunch before, and it was fine every time, but the first day, the one time I do it, exactly. So, but hey, I'm definitely far from perfect. So, as you can see here, though, the sync duration is almost 3 times as long as the async duration. So, it's a clear performance gain to using the async approach here. So, this is a more probably like, I guess, common example. People probably use synchronous or asynchronous functions to deal with file I/O. But the other example, kind of going back to the beginning of the presentation, is going to show how we can use the ideas behind concurrency to improve like user interactivity, specifically with your application. So let's go ahead and take a look at that. So along with this, go to our front end. So I just have a simple React application. Nothing too crazy.
Can I ask a clarifying question?
Yes.
Just to make sure I'm understanding why that's running 3 times slower. So you're talking about it has non-blocking I/O, so is the reason that async is faster because async blocks processes until it's done, correct? Or how does that work? Maybe I'm misunderstanding.
Gotcha. So what do you mean when we call the await statement?
Yeah. Basically, synchronous versus asynchronous. If asynchronous is more performant, it's because it just gets that work done before it does anything else. Or
So in the context of that last example, what's kind of happening is when we use like the await statement, what's kind of going, it looks like it's similar to it looks very similar to the sync function. Thank you for asking this question. It's actually a really good question. Is that the async await is actually syntactic sugar for like basically promise out of that. So what's happening is when we call the read file async, we're actually offloading that promise to a later point. And then so the main thread is now available to do more work, whereas the sync method, it's essentially kind of like, you can think of it as doing a while loop, right? It's just blocking the main thread. Whereas the async, even though it looks very similar, it looks like it's blocking with the await, is actually turning it into that function call into a promise, and it gets eventually added back to the task queue once it's settled. So, and settled means when it's either resolved or rejected. There's a bit of nuance to this promises actually end up in a micro task, which I can maybe talk about a bit later. But for the sake of this portion, you can think of it just as being into the task once it's settled. So, yeah, question?
Yeah, it's kind of a related question. I also am not super strong in JavaScript. But so going back to the example you had about the cook in the kitchen, right? So I noticed for async and sync, you make one call to each. So like, if you compare that to the example, like, when cooking the steak, like even if you as a cook went to go do something else, you know, if you only have one order,
yeah.
Why is that one order faster asynchronously? Because you're not shifting tasks. I expected you to continue on and do like 100 calls if you're local, and I didn't see that happen, so I was super curious.
That's a good question. I probably didn't clarify very well. So the benchmark code, I'm sorry, I kind of brushed over this pretty quick, but the benchmark code actually loops through, so the MD files gets all of the files in this directory, and then makes an individual request to that endpoint for each file.
Okay, so you probably made like 30 calls.
Exactly.
Okay, so I was wondering why
yeah,
that was
sorry.
faster.
So that might,
okay, no,
yeah, yeah, that wasn't immediately clear, but yeah, that's essentially what's happening. So that's how we're making all the concurrent requests occur. That function loops through all of the markdown files within the assets directory. So we're actually making a bunch of requests. So yeah, thank you for the question. So okay, back to the front end example. So this is obviously a really basic UI. So it's just a few buttons. Page 1 tab and page 2 tab, and then the view items button. And the view items button is the interesting one. Essentially, what I've coded was if you go to the items component, the items tab itself. Each item, so we generate 500 items, which is just simply a string with an item followed by a hashtag and a number. And then we map the items tab, just basically gets all of these items, which we generate 500 of them. And then we create an individual item for it, which is just, again, a list item. So you have one order list with a bunch of list items. And the way I artificially slow things down is that I make the each item wait 2 milliseconds using this while loop. So it's going to be very slow, and it's going to be a really bad experience, which is what I want. So let's take a look at that. So let's flip around, and that's terrible. Which is good, and for this, I want to do that. So obviously we can intuitively see that the experience is quite poor. But let's take a look at the Chrome DevTools to get a sense of like the impact, right? And again, I mentioned interaction to next paint. So the way we can look at or calculate interaction to next paint is we can use the Chrome DevTools. And under Lighthouse, we change the mode. By default is navigation, but we can change it to timespan. So if you click on timespan, you can Once it says you can interact with the page, you click around and do things, and it'll report a bunch of metrics. So I'll click around and do this. These look good. This is really bad. And so and the time span will tell us the INP value as well as the total blocking time and another statistic. So as you can see, interaction next pane is not good. So over 2,000 milliseconds, so about 2 seconds before you can actually interact with the page again. For context, a green score is under 200 milliseconds, so that's 10 times more than like the very highest good score. And then yellow is from 200 to 500 milliseconds. Anything above 500 milliseconds is red, so we're quite a ways above anything remotely good. So how can we make this better? So going back to what I was saying earlier in the presentation, React has introduced this, the concept of concurrent React with React 18. And in particular, there's one hook called use transition, which allows you to mark certain state updates as non-blocking. And before actually I implement that, I should maybe go into a bit more context as to how I'm actually implementing the tab selection. This can be useful context. So basically, I have a state variable called tab, which refers to the different tabs. I call them page 1, page 2, and page 3. And so I just have a type here that references the different values for what the tab could be. And then this function tab view just has a switch, which returns, in the case of page 1, page 1 tag with page 1, so forth for page 2, and then finally an items tab. And so I have a function called select tab, which is used to handle the on-click events for the logins. So again, right now, this one right here is very slow, but we can, again, improve the performance by using the use transition hook. So I'll work at implementing it. Before I actually demonstrate the performance boost, I'll kind of just talk about why it is beneficial. So the use transition hook returns a tuple with 2 values. The first value being a boolean called pending, which is showing that it represents whether or not the state update is still running, still occurring. And then you can use that to conditionally render like a loading widget. So which we'll do just that. So do is loading. Yeah. Oh, sorry, it's pending. Okay, I'll do just a little H1 loading. Okay, so I've added the pending, and I have to actually use the start transition. So the second value within this tuple that's returned from use transition is a function called start transition. And what you do with this function is so the function itself, when you call it, accepts one argument, which is a callback function. And within this callback function, you just wrap whatever state update that you make in this function in this callback. So in this case, the state update is set tab, and what this will do is mark this interaction as, or the state update as interrupted. And so the benefit is essentially that when you click around now, if you click on the view items and it's really slow, previously it was really slow, but now if you click somewhere else, it will allow, React will essentially interrupt this process and then perform another state update or do something different. So let's see how that looks really quick. So let's go click around. If I did everything right, it should be a lot quicker. As you can see, it's very interactive now, which is really nice. And as you can see, you still wait the duration and then eventually the items appear, which is really cool. So, and let's take a look at another IO score and see how the INP value looks. Let's look at the time span. 5.5 page, okay. So click here. Let it fill up the page. Okay, cool. And then we should get a good INP score. Yep. So as you can see, that is quite a bit better than 2,000 milliseconds. There's no total blinding time, which is great.
So is that a book waiting for all those items that you result before you kind of make specific design?
That's a good question. So we'll look at it in just a second. So I have some theories or a hypothesis as to why it works the way that it does. I don't know the exact underlying implementation, but we can kind of glean some insights looking at the performance tab. So that's actually a good segue. So we look at the live scores, which tell us basically, you know, what the interaction XPan is, but we don't really know like what is occurring more like concretely. So, or more granularly. So using the performance tab, we can actually record our interactions and look at stuff like the main thread to see like what operations are occurring on the main thread and so forth. So let's go ahead and do that. So I click on this and I can start recording. I can start moving around and this. Okay, it's loading. I'm gonna stop that. And okay. So here's what we see. So as you can see, there's like these big chunks of blocking time within the main thread, but if you zoom in, they're kind of chunked up. So, and as you can see here, you have an interaction and mouse click. And this mouse click corresponds to when I click on page 2. So here's what I believe is happening. So going back to the idea of like the single threaded event loop, tasks live in a queue, right? And so one thing I didn't mention was that depending on the implementation, there can be multiple task queues. So the browser has more than one task queue because some tasks are more high priority. So running a script tag is lower priority as opposed to a mouse click. So when I perform a mouse click, it's going to prioritize the mouse click event. And then for the script tags, what I think is happening here too is you would expect though if everything was in queue right away, right? So say this big chunk of work that, okay, well, yeah, the mouse click takes precedence over it, but if you were to add all of the work for this thing in a queue, wouldn't you see it being run in the first place? My guess is what's happening with the use transition, or start transition function, is that it only adds another task to the queue after it finishes the chunk. So another chunk adds a task to the queue, but then in the meantime, if another process occurs, it will kind of, the mouse click, it will take that will take precedence over the previous update. So that's kind of, well actually before I move on, I kind of want to also go back to when we did have the start transition function on our RC update, just to see what it looks like in performance tab. Okay, here we go. So as you can see right away, the task is one giant block. So it's not those nice little segments that we had before, where the event, the JavaScript event loop had an opportunity to respond to another request coming in. So this is essentially the equivalent of clicking state and not doing anything else for 6 minutes. So yeah, that's kind of like the gist of it for the use transition hook. There's one other approach to doing this kind of work that is not React specific. And it's a relatively new approach using an experimental API that Google has introduced called the Chrome team has introduced called the scheduler.yield function. And so I can kind of demonstrate that. It will do something very similar to what you see here, but the scheduler.yield function will, is a function that returns a comment so you can await it. And it's not, again, not specific to React. So you have another segment of code that runs synchronously typically, and it's blocking for long periods of time. You can use scheduler.yield to prevent it from just taking up hogging up the main thread the whole time. So let's take a look at how that might work for this situation or this example. So what I'll first do is show scheduler.yield tab. So right now there's no implementation for it, but we'll go ahead and build that up a second. And so the distinction is before we have the timeout here, or the artificial slowing down of each component here. And then for the scheduler.yield, again, this is a very contrived example, so it doesn't make the most sense, but bear with me. We have this generate items async, which is doing the same thing, creating these items. But now the blocking is occurring during this generation function. So this is not a React function, or it's not a React hook or anything, not a React component. So, but this will work outside of React. So to access the scheduler API, you can use it's gonna be in window.scheduler. So I like to always just add a check for stuff like this. So you can scheduler. Even though it's not really needed. Oh, one thing too, if you were to try to do this or run this code, you'd get this error. Unless you went to the Chrome flags and enabled the experimental flag to use the scheduler function, the scheduler API. Alright, so, and then the scheduler, the one function we care about from the scheduler is the yield function, so we'll just say, and then by default it's going to be of type unknown, so we'll just cast it as yield, which is a function that takes no arguments, returns a void promise. Cool. So now I can use scheduler.yield to, during the duration of this little while loop, to yield the main thread. So basically handing back control, not having that big segment anymore, and telling the thread, okay, use something else now. Yield, I'll make sure I wait this too. All right, great. So before I continue, let me first also add the other tab. So I'll create a new page, print tab, scheduler. Let's add a button so you can click this. I also don't want to use this one tab because I want to just showcase the scheduler.yield on its own, so I'll just use set tab. So it's not wrapped by this direct transition. Alright. Let's go ahead and flesh out this basically the same as the other items component. So what we'll do here now is call this generate items async function. And so since it's async, I'll do something a little bit different. We want this to run once when the component first renders, so wrap it around a use effect. And we'll just add any dependency array, so they run multiple times. What we'll add here is we also want to add some state variables. So we want a state variable to hold the array of items. And then we have a loading state variable as well. Well, default it is true because when you first run it, we want to display the loading state, and then we'll add the set is loading false later on. So let's go ahead and update this too. So before I fill in the use effect, I just want to forget to actually render the items. So we'll do, before I do that, I should actually have the loading state too. So is loading H1. And then the snap will have a single argument, which is the item, a single string for each row. I'm missing something somewhere. Oh, okay, and now we have the actual rendering of the different parts of this component. Let's actually update the state. So we have the items when we go to this tab. So again, we're going to call this generate items async function. Data items. We actually have to do an async function because use effect has to be a synchronous function. So call 2 so don't forget. We'll call the get items async, which will return the array of items, or generate items async. Also want to make sure I await it here. And then now I have the array of items after they've been processed. And I can set that here. And then since we've loaded all the items, we're no longer loading, so we can change it loading to be false. Okay. I think this is good, but knowing me, I probably forgot to do some things, so it probably isn't going to work the way I expected to. But fine. That's just me consoling myself, so. Yeah. should probably give this a different name too, so I can actually differentiate between each one. All right, let's just click and see if it intuitively feels better. Oh, it looks good. Okay, perfect. So you might notice a little difference in behavior, and I can talk about that in a second. But let's just take a look at the performance that we have to see if we get the chunked up little pieces. Sometimes the profile can be up. There you go. Next thing. Beautiful. All right. So as you can see, we do have the chunked up little. They're really tiny. They're really, really tiny. So they're about 1 or 2 microseconds. They're really, really small. But you can see we have the chunked up work here. But you might notice some small distinctions, right? So I have a quick interaction here, but we're still doing the main thread work. So we're still doing the previous work before. And that's an intentional feature for the scheduler.yield. So this is probably not the greatest example to showcase its benefit. But the purpose of scheduler.yield is to make sure when you say have a chunk of like a big block of work that you want to run synchronously. Previously, you could use like set timeout to kind of yield to the main thread and let something else process. But in doing so, set timeout as another task to the task queue. And so now the order of work becomes all switched up. So scheduler.yield will actually resume right where you left off, which is a nice benefit. In this case, it doesn't make as much sense, so the start transition is a better approach to get this kind of behavior. But I just wanted to showcase that API as well. Again, it was, I think, introduced last August. Again, this is behind experimental flag, so I probably would recommend using this right now. But I thought I'd showcase it because that was kind of cool. So, yeah. Yep.
Yeah, it's probably kind of a simple question, but I'm just wondering, when you're using the use effect hook and setting up the fetch, you defined the async function inside of the use effect hook. Is there a specific reason for that, or did you just choose to do that?
I just chose to do that.
Okay.
No
Just want to
particular
make sure
reason,
if it
yeah.
needed to be a closure for some reason, or if
Oh,
it was just like.
yeah, that's a good question. No, there is no particular reason for that. I just want to do that. So
Great.
cool.
Well, I think you have to do it sometimes.
I don't believe so, because if you look at the use effect, I mean, it just has to be within the scheduler yield tab, because we rely on the set items to set its loading, but it could be here too, right? And the behavior should be the same. So, here. So yeah, it can exist out here. It just needs these values there, and that should be good. So yeah. Yep.
Would you say in the chef analogy that yield is essentially just a moment when the chef like looks up and around, and then I go right back to what they're doing and might see something else?
Yeah, I think that's a good, yeah, I think that's really good. That's pretty accurate because, yeah, without using the yield, you're basically, the chef is just monomaniacally focused on the thing in front of them and he's not looking away. But you're yielding, you know, stretching your back and you're like, oh, I see an order. Take it off and do that instead. So I think that's a very good analogy for that. So, yeah, any other questions? That is the end of the demo side. So if you have any questions, feel free. Yep.
As far as applications go, on front-end applications, it makes sense to not block the UI of the user experience interaction. What would some back-end applications be?
Of what part specifically? Like scheduler? Or?
Yeah, scheduler or choosing to clog up the main thread.
Gotcha. So the question is like, what are the applications listening to the scheduler on the back end, and when would you not want to block that back end as well? So for context, the scheduler.yield API is a browser-specific implementation. It doesn't actually exist in Node.js, for example. The reason why you want to be able to not block the thread on the back end is if again you have like file I/O operations. So going back to the example of reading the markdown files, there's like a period of time where the thread is idle because when reading from a disk or reading from other like some hard drives and storage space, it's not, the hard drive has to do work, right? And so during that time, the thread can do other work. The CPU is free to do something else in the meantime. So it just gives it the opportunity to really start something else. That's like the idea behind it. So yeah. Yes.
Are there any options within those either of those two options? to like explore using worker threads?
Sorry, can you please repeat that?
Something like worker threads or like other threads to do, like obviously outside of the main event loop, but still non-blocking using the same methods that you showed today.
Yeah, definitely. Like if you like, that would definitely be beneficial if you have several synchronous like, processes that you want to do like in parallel. So that would be definitely applicable. I think for file I/O, generally it's not worth the effort of spinning up another thread because again, there's a period of it being idle. So the single thread event loop can handle stuff like that very well. But yeah, but like you know, this example here on the front end, that could definitely be an web worker. So I think in that case, it makes sense to maybe offload it to a web worker, which creates another thread. And also, what was I gonna say with that? Well, the only downside with web worker is that you can't access the DOM, but if there's no need for the DOM, which was the case for this function, web worker makes perfect sense. So yeah.
Yeah, so I just want to make sure I'm understanding the concurrency versus parallelism. So concurrency, to reuse the chef analogy, it's like the chef hands it off to something else, or it doesn't need work done right now, so they go to do something else in the meantime. So they are only ever doing one task at a time, but they're picking up different tasks depending on what's ready. And in parallelism, it's like if you had multiple people in the kitchen doing something at the same time.
Correct, and like, so the question is going back to like a parallelism versus concurrency. And yeah, so I would actually say too, just to clarify, like you can have multiple chefs, in this case multiple threads, and still not have full parallelism. So another analogy we were kind of talking about, me and some friends talking about, is like, how many of you ever played the game Overcooked? Yeah, a couple of you play Overcooked. So you might have like, up to 4 people playing, but if there's only like, there's only maybe sometimes one like pan and one cutting board, so you can't have 4 people doing the cutting board work. So true parallelism is like everyone has like a pan that they can like sear stuff with, a chopping board that they can use to cut in a pot to boil something. That's true parallelism, where you have the ability to do everything equally, so the same exact operations at the exact same time. So yeah, good question. Anything else? I can also go into depth about other details of the implementation if anyone's curious, or yeah, feel free to ask away.
Nice job doing a live demo.
Oh,
You're doing great with us today.
Thank you, appreciate it. Well, it definitely wasn't perfect, but that's,
Worked.
yeah, it could have been a lot worse. So, I'm glad for that. So, but yeah, if there's no other questions or anything like that, thank you so much for stopping by, and yeah, feel free to come chat if you have anything else.